Hi folks, welcome back to Math with Captain Rod. The topic of this video is integration by parts. And one of the things I'd like to say about this first before I begin, is that integration by parts is an extremely important method for integration. It's a very generic method. It can be used on a lot of different things. It's not particularly difficult, but it's extremely useful. So anybody watching this video, this is a really good one to pay really particular attention to. All right, so integration by parts is based on the product rule of differentiation. If I looked at a pair of functions here, let's say u and v, where both of these are functions of x, right? And I say to myself, all right, u times v, I look at that product, and I differentiate it. So I'm going to put u times v prime. That's going to equal u prime v plus v prime times u. Now, I'm going to take this equation here and just kind of mess with it a little bit. If I move this term to the left, right, and then rearrange it, this is going to read u v prime is equal to u times v prime minus vu prime. And now if we integrate both sides, or we integrate everything, integral u v prime is going to equal integral u v prime minus integral v u prime. And the integral of u times v prime, right? Again, prime means derivative. This is a derivative and then an antiderivative. So this is just u times v minus integral of v u prime. And this basically is the formula for integration by parts. I like to write it in differential form instead. So what I'm going to do here, I'm going to actually start a new sheet, right? And I'm going to write in this form. Integral u dv is equal to u times v minus integral of v du. And this is the generic formula for applying what's called integration by parts. Now, again, where u and v are functions of x, the way you apply it is this. You have to choose a u. Whatever's left is dv. So you're going to choose a function for u. Whatever's left is your dv. Then you'll notice that the integral u dv, it's uv minus integral v du. So after you choose the u, then you calculate du, because you need it for over here. And you do that by differentiation. After you have your dv set, then you calculate v by integration. So again, whatever your u is, it needs to be a function that you can differentiate fairly easily. And then your dv, you want to be a function that you can integrate fairly easily. Once you choose your u, you know your dv, you then calculate du, then you calculate v, then the integral is equal to uv, that's this product, minus the integral of v du, that's this product. I like to work these out kind of in this order because the geometry of it helps me remember the formula and how to apply it. So the basis is choosing a u. Now, a long time ago when I took Calculus 2, I took it with a fellow named John Flugoff, who was a terrific guy, and he gave me this little acronym for choosing the u. I've used this acronym for 25 years or so. I have found it to be a very, very good tool for integration by parts. And the acronym is LI8. I'm going to write it down. And this is for choosing u based on this acronym. The L stands for logarithmic, the I stands for inverse trig, the A stands for algebraic, the T stands for trigonometric, the E stands for exponential. So what we're going to do is to choose u, we're going to be looking at our problem, and we're going to go through the LI8 here, and if I see a logarithmic function, that's going to be my u. If I don't, I look for other types of functions. If the first one I see is, say, an algebraic function like x squared or something, that's going to be my u. If the first function I run into is a trigonometric function, that's going to be my u. Whatever's left will be the du. I'm sorry, the dv. So you choose your u based on this acronym. That's going to go here. Whatever's left is your dv. That's going to go here. Calculate your du by differentiation. Calculate your v by anti-differentiation. Then the integral will equal this product, uv minus integral v du. Now you notice you still have an integral to perform. That's why it's called parts. You're doing it kind of like one part at a time. Whenever you integrate by parts, you end up having to work out two separate integrals. Integration by parts is a very, very powerful technique. It's wonderful, works very well. I want to talk a little bit before I end this video about when you use it. You typically use it when you're looking at the product of two functions that don't look alike. So, what do I mean by that? Oh, how about the integral of x squared sine x dx? Here's an integral that has two different functions, x squared and sine x. And when they're different types of functions, that's what I mean by they don't look alike. That's your clue that integration by parts probably will work. I might as well go through here and talk about how to choose the u. So if we go through this example, just choosing the u here, I look through my acronym here, Lie8. I look over for logarithmic functions. Nope. Inverse trig functions. Nope. Algebraic functions. Yes. X squared is an algebraic function. So in this example, we would say, all right, u is equal to x squared. Whatever's left is your dv. That's going to be sine x dx. Then you would go through and calculate du, and then you'd calculate v, and then you're going to integrate. I'm going to save the examples for another video, though, and I think I can just end this right there. So this is just meant to be kind of an overview of the method, and now we'll look at some examples. Have a great day.